In early algebra, you inevitably hit a specific wall. You are asked to solve for x in the equation x squared plus 1 equals 0. Rearrange that, and you need to find a number that, when multiplied by itself, gives you -1. When you multiply a number by -1, you take its position on the number line and rotate it 180 degrees around the 0 point. This diagram outlines the 90-degree dimensional leap. The top red arrow shows multiplying by -1. Because I is the square root of -1, multiplying by I applies half that physical movement. It pivots the number 90 degrees, straight up, off the standard line. Moving into a second vertical dimension is the only geometric way to resolve the paradox of the negative square root. By adding that vertical axis, we leave the 1D number line behind and enter a 2D arena called the complex plane. This breakdown shows the anatomy of a complex number, written as z equals a plus bi. The yellow arrow highlights the real part, dictating horizontal movement, while the blue arrow points to the imaginary part, controlling vertical movement. This graph charts exactly how those two components work together. Position vectors, like the pink one at 3 plus 4i, use their specific real and imaginary parts to plot precise locations on a two-dimensional grid. At this stage, complex numbers appear to be static markers. They function as 2D geometric coordinates, though they are written using the language of 1D algebra. This grid-based layout is known as the rectangular form. It treats the math like navigating city blocks. You travel a specific distance east or west, then a specific distance north or south to reach a destination. Adding two complex numbers is an active geometric translation. As shown here, the green vector, z2, slides the pink vector, z1, across the plane. The sum is the resulting diagonal of that movement. Subtraction follows the same mechanical logic in reverse. You flip the vector being subtracted 180 degrees and translate the position accordingly. While the rectangular form is useful for calculating these static positional shifts, it is cumbersome for more sophisticated operations like multiplication. Multiplying raw grid coordinates creates algebraic clutter that obscures the underlying geometric intuition. To solve this, we use the polar form. This image shows how a point is defined strictly by its distance from the center, r, and its angle of direction, theta, rather than horizontal and vertical grid lines. Ditching the grid reveals that complex multiplication is an active transformation. It is a command that changes the state of the entire plane. The mechanics are straightforward. You multiply the lengths of the vectors to scale them, and you add their angles to rotate them. This identifies the complex number as a verb. It is an instruction set that commands space to scale and rotate simultaneously. The exponential form treats this movement as a continuous state. Raising a complex number to a power applies that scaling and rotation repeatedly, resulting in compound motion. This image illustrates that repetitive action. As the number z is raised to the second, third, and fourth power, its length scales by that power, while its angle is multiplied, creating a geometric spiral. This spiral models compounding dynamic forces in the physical world, from the decaying orbits of satellites to the oscillating frequencies of radio waves. Exponentiation allows the complex number to model systems that change smoothly over time, moving the math beyond the limitations of a static grid. We can now unify these perspectives into a single framework, the rotoflex operator. This diagram shows the three identities existing simultaneously. A complex number is a static point in space, a physical vector with length and reflection, and a dynamic operator that scales and rotates. Expanding our perspective beyond the original 1D line proves these numbers are a necessary extension of geometry. They provide solutions that a single dimension cannot contain. Calculations in electrical engineering, quantum mechanics, and fluid physics rely entirely on this geometric language to describe continuous rotation and transformation. Complex numbers provide the foundational geometry for a physical universe defined by constant, dynamic change.